my warm welcome to Dr. Chetna Bongade ma'am, HOD Mathematics, Sri Shivaji College Rajura, Dr. Shilpa Samdurkar ma'am, HOD Mathematics, Vidya Vikas College Samudrapur, and Dr. Varsha Dange ma'am, Assistant Professor, Department of Mathematics, Sri Shivaji College Rajura in this conference. I welcome all the academicians, students, research scholars, and who have registered for this international webinar and join us on this virtual platform. Without taking much time, I would like to invite our dear principal, Dr. S. M. Warkar sir, to deliver the welcome address. Over to you, sir. Warkar sir.
Am I audible, Swarna?
Yes, sir, you are clearly audible. Proceed.
Good morning, dear friends. Sri Shivaji Arts, Commerce and Science College Rajura and Vidya Vikas Arts, Commerce and Science College Samudrapur District Varda have jointly organized today's international webinar on recent advances in mathematics. Inaugurator of today's online international webinar, an academician, Dr. Suresh Revatkarji, Dean, Faculty of Science and Technology, Gondwana University, Gadchiroli. Today's keynote speaker, Dr. Mahesha Narayana, the University of West Indies, the Mona campus, Kingston 7, Jamaica. Dr. G.D. Kedar, Professor and Head Department of Mathematics, Rashtrasant Tukdoji Maharaj, Nagpur University, Nagpur. Co-organizer of this webinar, my friend, Dr. Kishorji Revatkar, Principal, Vidya Vikas Arts, Commerce and Science College, Samudrapur. Our Vice Principal, Dr. Rajesh Kherani, Vice Principal of Vidya Vikas College, Dr. Naina Shirbhate ma'am, our Head of the Department of Mathematics, Dr. Chetna Bongade, Assistant Professor, Dr. Varsha Dange, Dr. S.W. Samudrakar, Head of the Department of Mathematics, Vidya Vikas College, Samudrapur, our IQAC Coordinator, Dr. Mallesh Reddy, Co-Coordinator, Dr. S.N. Sende, Ms. Swarna Nalge, and all online participants, research scholars, students, and professors who have joined this international webinar from different parts of the globe. As an organizer, I cordially welcome you all. It gives me immense pleasure that our maths department regularly organize various student-centric academic activities. I congratulate the department for their efforts. Dr. Kedar sir, Dr. Mahesha ji, and Dr. Revatkar sir have given their precious time to guide us on this very important topic. Dear friends, we all know amongst all branches of science, mathematics is one of the fastest growing branches. It has attracted the attention of researchers, scientists, engineers from academia and industry, in mechanical engineering, civil engineering, in robotics, as well as for finding inexpensive and fast computing, reducing cost and increasing quality, logistics and complex transportation management, analyzing big data and finding optimal solutions. This subject, mathematics, has played a very vital role. Application of mathematics is increased in day-to-day life also, for managing money, for balancing checkbook, for shopping the best price, for different such items like figuring out distance, time, cost of travel, for understanding how our loans, car loans, home loans, for schooling, playing music, etc. We need knowledge of mathematics. In addition to it, what are the new or recent advances in this subject, mathematics, that will be discussed today in detail by Mr. Mahesha ji and Kedar ji. Therefore, without wasting your precious time, I welcome you all again and hope this webinar will enhance our knowledge of mathematics. Thank you. Thanks a lot. Over to Suvarna.
Thank you, sir, for your inspirational and encouraging words. It's my absolute pleasure to call upon Dr. Kishore Chandra Revatkar sir, Principal, Vidya Vikas College, Samudrapur, to deliver his welcome speech. Over to you, Revatkar sir. Dr. Kishore Chandra Revatkar, sir.
Hello, Suvarna.
Yes, ma'am.
Unmute. Kishore Revatkar sir is unmute.
Sir, unmute yourself.
Revatkar, sir,
Revatkar,
your
sir,
mic is
unmute yourself.
muted. Your mic is muted. Please unmute yourself.
Now, I was not allowed to unmute myself. Now, okay.
Yes, sir. You are
Thank you, Suvarna madam, for giving me this opportunity. At the outset, I must thank you to Dr. S.M. Varkat sir and Dr. R.R. Kherani for giving this opportunity to collaborate for this international event. And once again, my heartfelt thanks are also due to all the organizing committee for allowing us to be a part of this international event. The Honorable Dr. Suresh G. Revatkar, who is Dean of Science Faculty of Gondwana University, Dr. G.D. Kedar Sahab, the head of the Department of RTM Nagpur University, Mathematics Department, Dr. Mahesha Narayana, who is from the university in Jamaica. I know about the Jamaica because they are producing a lot of good cricketers, but I'm very happy that today we are with us Mahesha Narayana, who will be definitely going to give 4s and 6 in the mathematics. So this event will definitely be a entertaining event and of course enlightening event, because we have these two members who are renowned persons in mathematics. Dear participant from the India and abroad, so I welcome you all on behalf of my college, Vidya Vikas Arts, Commerce and Science College, Samudrapur district, Wardha. Hope this event will definitely going to add to your knowledge. The deliberation that will be and the discussion that will be go on throughout the day in this event will definitely going to get something else that will be different from your regular mathematics. So with this word, I would like to conclude myself. Thank you for this opportunity.
Thank you, sir. Thank you so much for your worthy words. Moving ahead, I request Dr. Chetna Bongade, ma'am, Head Department of Mathematics, Sri Shivaji Arts, Commerce and Science College, Rajura, to put her introductory remark. Dr. Bongade, ma'am.
Good morning to one and all. It's my pleasure to welcome all the participants who have joined us for this one-day international webinar on recent advances in mathematics. Organized by the Department of Mathematics, Sri Shivaji Arts, Commerce and Science College, Rajura, in collaboration with Vidya Vikas Arts, Commerce and Science College, Samudrapur, India. Inaugurator of today's webinar, Honorable Dr. Suresh Revatkar of Science Faculty, Gondwana University, Gadchiroli. Respected Dr. Varkat sir, Principal, Sri Shivaji Arts, Commerce and Science College, Rajura. Respected Dr. Kishore Revatkar sir, Principal, Vidya Vikas Arts, Commerce and Science College, Samudrapur, District, Wardha. Our eminent speaker, Honorable Dr. Mahesh Narayana, the University of West Indies, the Mona Campus, Kingston 7, Jamaica. And our other eminent speaker, Honorable Dr. Ganesh Kedar, sir, Professor and Head, Postgraduate Teaching Department, Rashtrasanta Tukadoji Maharaj, Nagpur University, Nagpur. Respected Dr. Ladke, sir, Chairman of BOS, Board of Studies in Mathematics, Gondwana University, Gadchiroli. Our Vice Principal, Dr. Kherani, sir, Vice Principal of Shivaji College, Rajura. Miss Naina, Madam, Vice Principal of Vidya Vikas Samudrapur College, and our IQSC Coordinator, Dr. Mallesh Reddy, all the participants, research scholar and PG student who have joined us from the different states and of India. Near about 400 participants register for this international webinar. I heartily welcome today's eminent speaker, respected Dr. Mahesh Narayana. Despite of his health issue, he has accepted our invitation and he is spending our valuable time with us. So thank you very much, sir. I also heartily welcome our another speaker, respected Dr. Ganesh Kedar, sir. In his busy schedule, he accepted our invitation and spared our valuable time with us. Without his unstinted help and support, we could not organize this webinar. So thank you very much, Kedar, sir. Presently, we are facing corona pandemic. It has changes almost all every aspects of our life. So there is a transition phase in teaching methodology also. We are very proud to say that 3 years before, Department of Mathematics, Sri Shivaji College, Rajura, successfully organized offline national conference on recent trends in mathematics on 16 February 2019 under the guidance of Dr. A.C. Deshnukh sir, ex-Dean and Head of PGTD Department, Rashtra Sant Tukadoji Maharaj, Nagpur Vidyapeeth, Nagpur. Now, in this pandemic situation, we are taking the opportunity to conduct a one-day international webinar on recent advances in mathematics. The main objective of this webinar are to develop the ideas related to advanced mathematical knowledge and skills. Also, how to apply this knowledge and skill in familiar as well as unfamiliar situations. So I hope all of you will enjoy these two sessions. So thank you very much for joining us. Over to Ms. Nalge, madam.
Thank you, ma'am. Thank you for your introductory remark. I got an opportunity to introduce inaugurator of today's event, Dr. Suresh Revatkar, sir. Sir has worked as principal at Mohsinbai Zaveri Mahavidyalaya, Desaiganj, Vadsa, District Gadchiroli. He has worked on various authorities and bodies of Gondwana University, Gadchiroli, and currently he is working as a Dean, Faculty of Science and Technology, Gondwana University, Gadchiroli. Now I request Dr. Suresh Revatkar, sir, to deliver his inaugural speech. Over to Dr. Suresh Revatkar, sir.
Thank you, madam. Am I audible, ma'am?
Yes, sir, you are clearly audible. Please proceed.
Namaskar, namaskar, namaskar. Very good morning to all the dignitaries, scholars, and the students. I first welcome today's eminent speaker, Honorable Dr. Mahesha Narayana from the University of the West Indies and the Professor Dr. G.D. Kedar from the RTM Nagpur University on behalf of the Gondwana University, Gadchiroli. I heartily congratulate Dr. Varkar sir and Dr. Kherani sir, the principal and vice principal of the Shivaji Science College, Rajura, and Principal Dr. Kishore Chandra Revatkar and Vice Principal Dr. Naina Shirbate of the Vidya Vikas College, Samudrapur, and their team members for organizing such mega event, international webinar on the recent advances in mathematics. Mathematics is defined as the science of quantity, and this definition prevailed until the 18th century. Starting in 19th century, when the study of mathematics increased in rigor and began to address abstract types such as group theory and projective geometry, which have no clear-cut relation to quantity and measurement, mathematicians and the philosophers begin to propose a variety of definitions. Nowadays, three leading type of definitions of mathematics are called logicists, intuitionists, and formalists, each reflecting a different philosophical school of thought. Today, the concept and the theories of mathematics are being applied to the almost all aspects of the medical science. I think this webinar throw a light on various aspects of the recent advances in mathematics, which definitely helpful to the professors, teachers, scholars, and the students of the mathematics. Thank you. Thank you, ma'am.
Thank you, sir. Thank you so much for officially inaugurating this international webinar on recent trends in mathematics. Thank you so much. After this, I take privilege to invite first speaker of today's international conference, Dr. Mahesh Narayana. I request my colleague and IKC coordinator of Sri Shivaji Art, Commerce and Science College, Rajura, Dr. Malesh Reddy, to introduce Dr. Narayana. Dr. Malesh Reddy.
Very good morning to all. Respected dignitaries present on the panel, resource persons, organizers, and dear participants. It gives me an immense pleasure to welcome and introduce today's first resource person, a great intellect, Honorable Dr. Mahesh Narayana, sir. Sir has completed his Masters in Mathematics from Department of Mathematics, Central College Campus, Bangalore, Karnataka. Sir did PhD in Mathematics from Department of Mathematics, Gulbarga University, Karnataka. Sir has worked for different R&D projects of DRDO and DST. He also worked as a postdoctoral researcher at University of KwaZulu-Natal, Pietermaritzburg, South Africa. He served as an assistant professor of mathematics at School of Advanced Sciences at VIT University, Vellore, and at Department of Mathematics, MS Ramaiah University of Applied Sciences, Bangalore. Presently, Sir is working as senior lecturer of mathematics in the Department of Mathematics, the University of the West Indies, Mona Campus, Kingston, Jamaica. He has published 24 research papers in national and international reputed journals and 4 papers in conference proceeding, and also published 1 book chapter. His research has 621 citations in Scopus with 11 H index. We are very fortunate to have such a great academician and researcher with us for today's conference. I welcome Dr. Mahesh Narayana, sir, and request him to start the session.
Thank you, Dr. Malesh Reddy, for that nice introduction. At the outset, I would like to thank the organizer of this international webinar, Dr. Chetna Bongade, madam, and the respective principals of the colleges, Sri Shivaji Art Science, Shivaji Art Science, Commerce and Science College, Dr. Varkat sir, and Dr. Revatkar sir, principal of Sri Sai, Vidya Vikas Arts, Commerce and Science College. And this is a good initiative by both the colleges that they are coming up with such an event, which will be useful for faculties, researchers, and mostly students, not only for those 2 colleges, those who have been invited to attend online. And it has been one of the good things with the recent pandemic, which has brought people together on the online mode more frequently and in a large number. So that is the reason why we are able to meet online like this. Otherwise, for me, let's say if somebody wants to come to your place and deliver a lecture, it would mainly depend on a lot of logistics and things like that to personally come. So such events which are organized by online will greatly help. Even we are at our own places, but still we are able to deliver things. All right, so are you able to see the screen? I have shared my screen.
Yes, sir, your screen is visible.
Okay, thank you, madam. And yeah, so I'm going to talk about how to handle nonlinear problems in a simple way. And this is part of the research that we carried out in the last year. And it has appeared in a good journal, ZAMM. You must be knowing that journal of Wiley Publications. I shall share the publication details later on if required. And as Dr. Malesh Reddy and others have introduced, I come from the University of West Indies. I work as a senior lecturer of mathematics. And for some reason, if you want to contact me, my email ID is mahesha.narayana@uvmona.edu.jm. Okay, so feel free to write to me if you have any concerns regarding the talk, or otherwise in general, if you would like to write to me. Okay, so you could use this email ID. So my talk is outlined as these items. Like, first we start with the introduction, and I'll talk about a simple way of handling nonlinear problems with the help of differential transform method. And I will explain how to use differential transform method for initial and boundary value problems, and what are the issues that we come across when dealing with such a differential transform method. And finally, I'll try to relate what we did in the last year, which is application of differential transform to a real world problem, and final concluding remarks. Okay. Yeah. So before I start to how to handle nonlinear problems, let us understand where these nonlinear problems are coming from. Where do these nonlinear problems come from? So the nonlinear problems come from various models that that come from various disciplines, as pointed out by Dr. Worker in his initial remarks. Mathematics has tremendous applications. It has been applied to not only science disciplines and also to social science disciplines, economics, whatnot. So we got tremendous applications of mathematics and potential to use mathematical ideas to solve real world problems. So nonlinear problems basically come from real world problem. Okay. Real world problem. And we use mathematics as a tool to understand this. Okay. Mathematics is a tool to understand such real world problems. Right? And what do we do in, how do we use mathematics, by the way? So you start with what is called as a real world problem, which you come across in your discipline or in a day-to-day life for that matter. Use the knowledge of the laws or the observations that you make with respect to that particular problem, governing laws which are applicable to that. And with that, with the use of mathematical knowledge, you convert that into so observations or laws together with mathematics, you combine and form a mathematical problem. Okay, so you form a mathematical problem. And you solve the mathematical problem and interpret your results and see what happens. Okay, it's kind of a cycle. So you solve and interpret and see if the mathematical problem is best explaining what's happening around us. Okay, so this is what the cycle of mathematical modeling looks like. And the place where we are standing at the moment is this place where we have a mathematical problem arising from a real world problem. And this is where the nonlinear problems mostly come into picture. Okay, so this is the source of nonlinear problems. Okay, and mathematical problems can be of different types. So it could involve algebraic equations. Okay, so it could involve algebraic equations. It could involve differential equations. And again, in differential equations, there are different types of differential equations, ODEs, and then you have PDEs, and then you have stochastic differential equations, delay differential equations. There are so many things that can be used to model a real world problem. And there are also what are called as integral equations. And integral differential equations. Okay, so all combinations can be thought of. And the regime where we are interested is models that give rise to nonlinear differential equations, nonlinear ODEs and PDEs. And mainly I'll deal with only the nonlinear ODEs in today's talk. Okay, so today's interest is in models that come up, the models that arise from mathematical problems that involve nonlinear ODEs. Okay, so this is a brief introduction, like where exactly the nonlinear problems are coming. So one simple example that I want to mention here, and later maybe use that example to solve in a simple way. Okay, so you all have this idea of free fall of an object, right? So let's say an object is held here of mass m, and it is allowed to fall freely, and let's say it reaches the ground after some time. And suppose somebody wants to know what time the object takes to hit the ground, you can model this particular problem in terms of differential equation with the help of Newton's law of motion. Okay, so you can apply second law of Newton, which says that rate of change of momentum is proportional to the net force. Okay, so rate of change of momentum is equal to net force. Okay, and what are the forces acting on this object when it starts to fall freely? So there is weight which is acting downwards. Weight is m into g, and there will be a reaction force which is equal and opposite, and that will be against your w. Okay, those are the forces. And momentum, all of you know that it is mass into velocity, and velocity is the rate of change of displacement. So you could write this as something like d by dt. Mass can be taken out, so you have velocity that's equal to, so net force is mg, and reaction force acts in the opposite direction, so you will have a minus sign, and reaction force is given by some constant times velocity square. Okay, so it's usually proportional to velocity or square of the velocity. So we take the quadratic model, which is used for free fall. Okay, so if you substitute everything, so you have this relation. Okay, which is basically a differential equation, right? This one is basically a differential equation, and to this we can append an initial condition saying that at time t equal to 0, velocity is 0. So this particular equation together with this initial condition constitutes what is called as an initial value problem. Okay, so there are also called as boundary value problems, which come across, which arise from various physical phenomena, right? So I'm just taking an example from physics. The examples can come from anywhere. Okay, so they can come from chemistry, biology, or sociology, or anywhere. Okay, so it's not necessary that it is always modeled through differential equations. As I mentioned, it can be modeled through any other equation. So as I mentioned, today's interest is how to use a simple mechanism or simple tool to solve the nonlinear models that arise from real world problems. Something similar to what I mentioned just now. Okay. Okay, so let's review what are the solution procedures that we have to do this.
Roshni, na? Roshni.
Somebody please mute your microphone. I'm not sure whose microphone is on. I'm requesting you to mute the microphone, please. All right, so to solve the initial value problems or boundary value problems, there are many methods. So there are numerical methods, there are analytical methods also. So there are methods like single step methods or multi-step methods, for example, Runge-Kutta method and Adams method or Milne's method. All these are some numerical techniques to handle IVPs. Okay, and you could also use finite difference method and shooting technique and spectral technique, all these can handle boundary value problems very efficiently. And there are methods which are popular recently, which is known as homotopy analysis method and homotopy perturbation method. These two are recently popularized by the Chinese authors, Chinese researcher, who is Shijin Liao is one researcher, and so these are the ones who made this method very popular, and it has been widely used to solve nonlinear problems that arise from real world problems. But the thing is that they are in the form of a series solution, and you tend to you must have some large number of terms in achieving the convergence. Okay, whenever you write the solution in the form of series, we must pay attention to convergence and stability, right? So these methods will involve series which will require large number of terms to be to achieve convergence. There are also methods known as variational iteration methods, Adamian decomposition method. All are similar approximate analytical solution. And differential transform method falls to this category of approximate analytical solutions or methods. But how it stands out from the other methods, what I mentioned, is that it is very easy to apply on any nonlinear problem. Okay, so and it requires fewer terms to achieve the convergence. I will show how that is done. Okay, and it can be handled with the help of computer very nicely and easily. So that is the reason why I call this as a simple technique. So that's why my talk is how to solve a complicated nonlinear problem in a simple way. So this gives a simple way of solving nonlinear problems. When I say it solves nonlinear problems, it is not the method for all the problems. Okay, it can solve certain class of problems. There are problems which may not be amenable to even differential transform method. Then you'll have to see what methods can be best used. Okay, so most nonlinear problems can be solved with this. Okay, so I mentioned that this is one of the method which is a differential transform method. So we have been seeing transform methods in the recent past. And what is the use of transform technique? So as the name itself suggests, a transform transforms things from one domain to other domain. Okay, so usually the need of transforms were based on converting a difficult problem into an easier one. Okay, so you must have heard of integral transforms. Okay, integral transforms such as Laplace transform, Fourier transform, Mellin's transform. There are so many transforms, integral transforms. So a general integral transform will look like, I'll just write it as I acting on any function is equals to some kernel ksx into f of s ds. Okay, or it should be f of x dx maybe, yeah. So this is in the x domain, and this will be in the s domain. Okay, so one best example is your Laplace transform. So Laplace transform of f of x or f of t, whatever, is defined as integral 0 to infinity e to the power minus st f of t dt. Okay, so physically this t refers to time domain and this s refers to frequency. So you are switching over from one domain to another domain with the help of a transform. That is one use of transform. So you can switch between two domains. The other important aspect of transform is that if you start with a difficult problem and you apply a transform technique, it becomes relatively easier to handle. So if you think of Laplace transform, so what does it do? If you try to apply them on ODEs, ordinary differential equation, I'll say Laplace transform, it converts into a algebraic equation. And it is the perception that algebraic equations can be handled much relatively with much ease than the ordinary differential equations. So you're moving from a difficult problem of solving ODE to an easier problem of solving algebraic equation. And you do the inversion, applying inverse Laplace transform to get the solution of your problem. So that's how your transform technique works. And one of the earliest known transform technique, which you might have all used, is logarithms. So what does a logarithm do? It was devised by John Napier way back in, I'm not sure that it's 1600s or something. So what does a logarithm do? Let's say log, it converts the operation of multiplication into what is known as addition. So you apply log, so it converts multiplication to addition and subtraction, that is division to subtraction. So you have this log of two numbers, product of two numbers, log x into y is log x plus log y. Like that, log of x by y is log x minus log y. So you see, again, it's perception. For somebody, multiplication and division can be easier and addition and subtraction can be difficult. It's just a perception. But in general, so one regards addition and subtraction as easier tasks over the division and multiplication. You will have to need multiplication table and things like that to carry out these two operations. So there is a beautiful way of converting difficult problems into easier problems. So one known earliest used transform is a logarithms, and there are other transforms which does this task. So our differential transform method belongs to this category of transform techniques. But the thing is that it will be using differentials, okay, derivatives. And let's see how that is done, okay? And Chaitanya madam, please let me know when time is nearing. I may not pay attention to that. So I'll be continuing otherwise. So please remind me of the time. Okay. And I see some
No, you can
hand.
continue. You can continue.
Okay.
You can.
No problem, sir. Thank you so much. I see some hand is raised by Sanjay Latalwar. Do you have any questions, sir? And there is also other hands raised by people.
No question. Knowingly it is done.
Okay, okay. No problem. If you have any questions, feel free to stop me at any point of time and ask, or you could also ask after, note down your questions and ask after the lecture. Okay, so yeah. So let's now move on to understand what is differential transform method. And it was Zhou, a Chinese researcher, maybe an electrical engineer, who, I mean, in literature, it is being projected as he is the first one to use, but actually before 1986, Russian researcher by name Foucault, he also is an electrical engineer. He has come up with this differential transform technique, but Foucault's work goes unnoticed, and many researchers quote Zhou and say that Zhou is the first one who. Such things happen in science. So some people would have invented something much earlier, and later somebody documents it, then credit goes to the one who documents the research. Okay, so it's Foucault, as I mentioned, a Russian electrical engineer who devised this transform technique. So what are the, I'll briefly tell you what are the advantages of this method. So method is applied directly to nonlinear problems without requiring any linearization, discretization, or perturbation procedures. Another important advantage is that it is capable of greatly reducing the computational work while still accurately providing the series solution with a faster convergence. And differential transform is free from discretization errors and it's good approximation to closed form solutions with less number of terms, that is. Okay, and it is a semi-analytical, semi-numerical technique which does not need the presence of small parameters like perturbation technique. It wants presence of such small parameters. If it is not present, you artificially introduce a small parameter into the problem and use the study. And perturbation method, if the perturbation parameter is not so small, then it would require a whole lot of terms in the series solution. Okay, so these are some of the advantages of differential transform, and how it is defined is using 1 and 2. So the kth order differential transform is defined as kth derivative of u at x equal to x naught divided by 1 by k factorial. And inverse differential transform is defined as a series 0 to infinity uk x minus x naught power k. So this you are moving from x domain to k domain with the help of differential transform. With the help of inverse differential transform, you will be moving from k domain to x domain back. And the k domain and x domain, they don't have any physical importance in this case. Something like Laplace transform or Fourier transform, where one domain represents time, the other domain represents frequency. We don't have any physical meaning attached to these domains. Okay, and if you look at these expressions carefully, you must be thinking that I'm fooling you by writing a Taylor series of u of x about the point x0 and calling the Taylor coefficients as the differential transform. And that is exactly being done. Okay, so it's nothing but the Newton's Newton's expansion, series expansion. Okay, I'm sorry, not Newton, Taylor series expansion. Okay, so the Taylor series is being written in this transform way so that we can apply it on any nonlinear problem. And when it comes to Taylor series, and you know how simple it is to evaluate Taylor series of a continuous function which has continuous derivatives. Okay, so yeah, so 1 and 2 are known as differential transform and inverse differential transform of a given function. And if you apply this definition to some elementary function, and for all this, your x0 is taken as 0. Okay, that means it's a Maclaurin series. If you have a polynomial function like x to the power n, uk will be the Kronecker delta function. So this is Kronecker delta function, which assumes value 1 if k and n are equal, assumes value 0 if k and n are different. And if you have an exponential function, its differential transform will be lambda k by k factorial. And lambda k by k factorial nothing but the Taylor coefficient of e to the power lambda x in the Taylor series expansion. And if you have sine, then the uk, the differential transform is given by this. And if you have cosine, you have this one. Okay. Okay, so we will look at, I mean, all these can be evaluated with just the help of equation number 1. Okay. So you differentiate k times and divide by k factorial, you will arrive at all this. And looking at the properties of differential transform method, you have the linearity property, which comes from properties 1 and 2, that your transform is like your integral transform, it is linear. It preserves sum and it preserves scalar multiplication. Okay. And when you have a product of two functions like v and w, and you will have to use some kind of convolution of v and w to get the transform of. And this is one of the very important property of differential transform, which helps to handle nonlinearity of the algebraic type. Okay, so it helps us to handle nonlinearity. And if you have a derivative of mth order of a function, then the differential transform is, I'm sorry, this should be a small k. Okay, so all these again can be obtained with the help of your definition. So I have just shown, the fifth property is for partial derivatives. I just omit that because we are not dealing any partial derivative differential equations in this talk. Okay. So if you have property 1 and property 2, they can be proved easily with the help of differential transform definition. So it's a kth derivative evaluated at x0 divided by k factorial. Substitute for u and u as v plus or minus w and carry on the differentiation. Because differentiation is linear, you'll get differential transform to be linear as well. And the convolution property is also proved, and it comes from Leibniz's rule of differentiation. That's also very easy to prove, and proof is given in this particular slide. And you have the other property of transform of derivative. If you have a u, which is mth order derivative, then the transform is given by k. Suppose, okay, I'll write down what is if u, what is differential transform of if u is equals to, let's say if u is equals to some dy by dx, then what will be u of k? So it's a first derivative, so you'll have k. So first derivative means there will be only one term in the factor. It will stop at k plus 1, okay? It will start and stop at k plus 1. So k plus 1 into y of k plus 1, where y is the uppercase y is the differential transform of this function 1. So if you have second derivative, then your u of k will be, so it will start from k plus 2, okay? So it will start from k plus 2 and end in k plus 1. So it is k plus 2. So this 1 is refers to the order 1, and this 2 is refers to this order, okay? And it will end in k plus 1. The next factor is k plus 1. So y k plus 2 you have, okay? Again, this one is all right. So this is how your uk plus uk, that is the differential transform, is calculated for derivatives, okay? And yeah, so with this, let's apply differential transform to one of the IVPs that I talked about in the earlier slides, okay? So we will take up this problem of free falling, okay? Which is governed by the equation dv by dt times m equals mass into acceleration due to gravity times some a times v square, okay? And initial velocity, you can take it to be some v naught, or it can be taken as 0, okay? Okay, so when the object falls freely, it attains what is called as a terminal velocity. A terminal velocity is a uniform velocity. After a certain large time, it attains a uniform velocity, and that is obtained by forcing the time derivative to 0, okay? So if you force the time derivative to 0, you have mg minus av square. So I'll call this as a infinity square, v infinity square, because it's a velocity at large time, okay? For large time, you'll have this derivative 0, okay? And you can solve for your a v infinity, and it is given by mg divided by a, okay? So one could use what is called as non-dimensionalization and try to put this equation in a simple form where all these physical parameters will be grouped into one, or it might perhaps disappear, okay? So your t can be scaled with velocity. Velocity, remember, it has length per time, and if you divide that by length per time square, which is acceleration due to gravity, you get a time scale, okay? So which is of scale unit time. And if you use your velocity and scale it by this v infinity, this equation will nicely look in this form, okay? and V star 0 equal to 0. And you could omit asterisk for simplicity and consider this equation as we may write this as dv by dt equals 1 minus v square, v of 0 equal to 0. Now I'll just illustrate how to apply differential transform to this particular problem. Okay. So let's say we apply differential transform. I'll denote D as differential. D stands for differential transform. So if you apply, what do you get? D of dv by dt is equals to d of 1 minus v square. Okay, and if you use the property, this is property number 4. According to property number 4, differential transform of derivative is k plus 1 times v of k plus 1 for first derivative. Okay, here uppercase v stands for differential transform of lowercase v. Okay, and the right hand side, it's differential transform of 1 if you use the linearity property. And what is differential transform of 1? 1 can be written as t to the power 0. Okay, 1 can be written as t to the power 0, and you apply that t to the power n formula. You had mentioned, we had mentioned it. Okay, so t to the power 0, so it's going to be n equal to 0, so it's going to be delta k. Okay, so the first one gives delta k, and the second one we'll have to use the product rule. Okay, which is here. So here v square, so v into v you have. So v into v means summation vk minus m wm. Instead of w, it is just repetition of. So I'll just use that here. Summation k going from, or m going from 1 to k, v k minus m times v. Okay, and in case of initial value problem, the initial condition gives you the first coefficient, first Taylor coefficient. Okay, and the rest of the coefficient, so this gives us, provides first coefficient, and this one is known as the recurrence relation. I'll just write one more step. So vk plus 1 is equals to 1 by k plus 1 times delta k summation m equal to 1 to k vk minus m, and this is known as a recurrence relation. Okay, this one is a recurrence relation. And it provides the value, other coefficient, rest of the coefficient, provides the rest of the coefficient. All right, so if you use the first one, okay, and calculate the first, what will be the first coefficient, students? Sorry, audience. So the first one will be v0 equal to 0. Okay, so from this you end up getting the first coefficient, which is v0 equal to 0. Okay, and rest of the coefficients are obtained from here. Okay, so u1, you put k equal to 1 in this recurrence relation. Okay, if you put k equal to 1, you get v1, which is equals to 1 by 0 plus 1 delta 0 minus summation k is 1, right? So m goes from 1 to 1. V k is 1, so v minus m. So that means m goes from 1 to 1, so you have only one term, and delta 0 is 1 because it's delta k. Delta k is delta k minus 1 is what? It is equal to 1 if k equal to n. So this delta 0 will be 1 only for k equal to 0, that is. For all the other things, it will be 0. So this is 1. K equal to 0, it produces value 1. And the other one is just v1 times v0. 1 minus 1 is 0, and you get oh, that is v0, I think. M equal to 0. This goes from 0 to 1. Yeah, I'm sorry. Yeah, if you look at this expression, it is going from 0 to k. So k is, yeah. So you get v0 when you put m equal to 0, what do you get? You get v0 v1. I think it is yeah, I think you should put k equal to 0 to get this, because it is k plus 1 if you see it here. So you want value 1 means k should be substituted as 0. Okay, k is 0, so m goes from 0 to 0. I'm sorry for that mistake. Okay, so m goes from 0 to 0, so there's only one term, and this will provide the value to be 1 if you simplify. So now you put k equal to 1 in that recurrence relation. So then you get v2, which is 1 by 1 plus 1 delta of 1 summation m going from 0 to 1 yeah, I'm sorry, this is also 0. So 1 minus m v. Okay, if you simplify this, you'll get this as 0. So like that, you calculate the other values for k equal to 2, 3, and so on. Okay, so you get v of 3 equal to negative 1/3 and so on. Okay, so you go on calculating this coefficient. Now the question is how long you want to continue, how many coefficients you need. So you could take sufficiently large number of terms so that the convergence happens. I'll just show the MATLAB code and run this. Okay, now the question to be addressed is how many terms should be taken in the series, because it's an infinite series, right? How many terms to be taken? So as I said, as many terms it required for convergence, or you can improvise on this by considering what is called as Payday's approximation. Okay, Payday approximation, where you write an infinite series, you approximate it with a rational function. Okay, with let's say nth degree polynomial on the numerator and another mth degree polynomial in the denominator. Okay. So the convergence can be achieved with less number of terms. Okay. For example, Payday 2, 3. What does that use? Payday 2, 3 will use a quadratic polynomial in the numerator and cubic polynomial. Let's say a1, b1, c1, a2 x cube or a3 x cube, or you could write it as a1, a2, a3, or a2, a1, a0, then b3 x square, b3, b2 x square, I'm sorry, this is x cube, b2 x square, b1 x plus b0. Okay, so you could use something like p23, which is and equate that to the infinite series and calculate these coefficients. Okay, and that will be the 2, 3 approximation. Like that, you can go for 4, 5 approximation or whatever. Okay, and I will run this MATLAB program which we have done, and I'm just going to share that particular code. Okay, so here I hope you are able to see the code. Okay, it is programmed this sum equal to sum plus uk minus r, and then you're adding the Kronecker delta thing outside. Okay, it approximates whatever we did with respect to this particular problem. Okay, I'll try to run this. I don't have time to go through in detail of the code. Maybe sometime else we can discuss. Okay, so if I run this, I think it is not running while sharing. I think let me unshare and then share only the plot. Okay. Just give me 2 minutes. It's trying to load. So I'm trying to run this. So it gives you the coefficients, and this happens to be the Payday approximation, 2-3 Payday approximation maybe. Let me take you to the plot, okay? So let me take you to the plot. So this is the output of the graph, okay? Output of the code, MATLAB code, okay? So what you observe here is this problem has a analytical solution, or exact solution. So exact solution of this problem is v of x equals, yeah, I forgot to tell you, once you obtain all these coefficients, you get the series by inverting, like summation vk x to the power k, k going from 0 to infinity. Okay, so that part I did not mention it here. So this, when you substitute all the, you get an infinite series, okay, all the coefficients. So the exact solution for this problem is tan hyperbolic t, okay, which satisfies the initial condition y0 equal to 0 at this particular point, if you see. And the green dotted curve is the 2-3 approximant, okay? Payday 2-3 approximant, like the infinite series is approximated by a rational function like this. And the black one, the black dotted line, which is almost merging on the red one, if you carefully observe, is the Payday 4-5, okay? So Payday 4-5 approximation, so gives you a better result. I'll just say Payday 4-5 of this, I'm sorry, it should be t. Payday 4-5, did I write x? Yeah, everywhere it should be t, I'm sorry. So Payday 4-5 will be a better approximate for your exact solution v of t, okay, which is tan hyperbolic t. And that's what this plot shows, okay? So this is about the initial value problem. And similarly, we could use differential transform with slight modification to boundary value problems. If you need more details, I'll share one of my master's students' dissertation, which is documented for all the other problems, okay? So I can pass it on to Chaitana madam, and you can collect it from her. So for lack of time that we have, so I'll stop taking further examples and take you to the one of the research work that we did recently, okay? So I'll stop share this one and share the other okay, so we were able to successfully apply whatever I discussed so far with the textbook example of free fall of an object. We could apply it to some Darcy-Brinkman convection problem that arise from real world problem, and it gives rise to what is called as boundary eigenvalue problem, okay? So the boundary value problem, boundary eigenvalue problem will have a non-trivial solution for some particular value of an eigen of a parameter which is known as the eigenvalue, okay? So differential transform method is used to solve that particular eigen boundary value problem. And how that is done, I'll show you. So general boundary eigenvalue problem is written like this. And you could say it's a linear problem. Where is the non-linearity that you are talking about? So the lambda, which is an unknown here, and y is also an unknown, the eigenfunction. So you will have a product of the unknowns. So that product of unknowns can be regarded as non-linearity, and you could deal with lambda as a additional unknown, and for that you can create additional artificial equation and boundary condition and solve that as a boundary value problem. So I don't know why the screen is not moving. Okay, so here is a physical situation where the lower plate is heated, which is at y equal to 0, and upper plate is maintained at a lower temperature at T naught. Okay, so there is a fluid in between these two plates, and there is a convection process that happens. Okay, and this convection sets in after a critical temperature is provided. Okay, and we are trying to determine what will be the critical temperature in the form of scaled non-dimensional number, which is Rayleigh number. And Rayleigh number in this case acts as an eigenvalue problem. Okay, so it is taking a while to move. I don't know what is the reason. I'll just close this and reopen. Just give me a minute. Are you able to see the screen, dear participants?
Yes, sir. Screen is visible.
Okay. Yeah, now it's moving freely. Yeah, so the problem is governed by equations 4, 5, 6. I'll not get into the details of physics part of it. I'll just move straight away, and these are the boundary conditions. I'll just straight away move to the mathematical problem where we are trying to apply this. Okay, all this we have seen. Okay, so the mathematical problem to which it is applied is this particular equation 41, 42, 43, 44. So the equations from 41 to 44 comprises what is called as an eigen boundary value problem. And this RA, which is to be specific, a Darcy-Rayleigh number, which serves as the eigenvalue of the problem. So eigenvalue for some particular value, you will have a solution Fn and Gn existing. Okay, so our aim is to find out Fn and Gn and also Ra. So there are two unknowns already, F and G. Your Ra will also be regarded as additional unknown. Okay, so there will be three unknowns altogether. And yeah, by treating Ra as unknown, you'll see that this particular term is a nonlinear term. Okay, and what does that mean to our Just give me a second. Okay, so yeah, other parameters are of physical importance, like dA is a Darcy number, lambda is a viscosity ratio, and so on and so forth. B is the Biot number. So don't worry too much about those. So how it is handled, I'll just tell you. So you have a fourth order differential equation here, and a second order differential equation. So it will be converted into 6 first order differential equations, and we will provide an artificial differential equation for RA also. So there will be total 7 differential equations. I'll just take you to the 7 differential equations. Yeah, here is the 7th order differential equation, and your RA is treated as the eigen, which is eigenvalue is given when you differentiate RA, you get 0, right? So that is the artificial differential equation, and initial condition is taken also as RA. Okay. So you have the differential transform applied to all those 7 equations. So we'll form a system of recursive relations like this. Okay, and here are the initial conditions. If you see, so the initial conditions U0, 0, U2, 0, alpha, all these are used to obtain first few coefficients of the differential transform series, okay, or the Taylor series, you can say. And that is obtained with the help of these recursive relations. So you will be able to get a solution in this form as a series solution in terms of y. Y is the independent variable. So I'm just showing you the expression here, which is a result of those recursive relations. And you could use them to analyze what's happening, and you can find out Rayleigh number, and you can see that Rayleigh number as a function of number of terms in the series. So you should take a minimum of 12 terms in the series just to ensure that RA converges. So beyond 12, RA value does not change. As you see, it is maintaining a constant value. So that means after 12 terms, however many number terms you take, RA remains constant. So there is a minimum of 12 terms which is required for the convergence. And other methods may involve more terms to achieve convergence. And the convergence of eigenfunctions are also shown here as a sequence of partial sums, and they also converge nicely. And k equal to 4, that is the black one, is the starting one. And as k equal to, all of them merge in this particular band, okay? Yeah, so these are nice results that we got. And we also compared our results of Rayleigh number with MATLAB inbuilt solver. And you see that they both produce exactly, close values, very much agreeing to each other, right? And yeah, so the other plots are from the physics point of view. I'll just skip them. And conclusions for this study. Differential transform has good accuracy and convergence and needs about 20 terms or less for achieving convergence. That's what I have mentioned through other example also. So one could improve on this convergence by using phasor approximation. We did not use that for this particular problem here. And results obtained by differential transform and the inbuilt routine B4C match very well, which validate the result. And external convection has a destabilizing effect, and slip Darcy number as a stabilizing effect. Those are the conclusions. Last one is from the physics point of view. Okay. And yeah, this concludes my presentation. I have used these references, and I can share this paper also, where there are more details provided about the method. And also I told I can share the master's dissertation of my student, which also has many details. Those of you who are interested can pursue further and learn more. Okay. I don't think I can cover everything about differential transform in this talk, but at least I have given you the idea and its potential to solve nonlinear problems, and how to handle convergence issues when it relates to series solution. All those things I have briefly discussed. Hope this talk has ignited some of your interest, and I'm always you can write to me to the email ID that I've given to you, and discuss in future if you need any help in this regard. I open myself to questions now, if there are any. Thank you so much.
Thank you, sir. Dear participants, if you have any question, feel free to ask. If you have any query, you can ask, or you can drop your question in chat box. Your participation is important for us. Let me check, sir, is there any question in the chat box or not?
Yeah.
Yes, one question is seen, sir. It is from Akshay Nerkar. What are the applications of cosmological models?
Cosmology is something related to astrophysics, and I really don't study problems from astrophysics, because I am a mathematician who do some modeling related to physical problems like convection and fluid flow problems. Okay. Yeah, cosmological models. There also you could see some fluid mechanics coming into picture, because in stars, what are called as stellar convection happens. The convection happens in a large scale. Okay. Those are called as large scale convections. And what I presented in today's talk as an application of differential transform is a small scale convection, which you can see in the laboratory. Okay. And similar result can be escalated to large scale convection, but that is a entirely different scenario. One has to deal with that separately. Okay. Yeah. Thank you so much.
Yes, sir. Mathematics gives us every reason to hope that every problem has a solution. Thank you, Dr. Mahesh Narayana, for an enlightening presentation on how to handle nonlinear problems in a simple way. Your knowledge in this area is really appreciable, sir. Your comprehensive talk and way of illustrating different problems using variety of examples would have definitely cleared all the concepts of those math students who have joined here. Thank you once again, sir. Now let's move ahead. We have Dr. G.D. Kedar, Professor and Head Department of Mathematics, RTM Nagpur University, Nagpur, as a keynote speaker. And to introduce Dr. Kedar, I request Dr. Shilpa Samdurkar, ma'am, Assistant Professor, Department of Mathematics, Vidya Vikas College, Samudrapur. Over to you, Dr. Shilpa, ma'am.
Thank you, madam. Am I audible, madam?
Yes, ma'am, you are clearly audible.
Okay. Good morning to one and all. Today we are fortunate to have with us eminent personality of Rashtrasanta Tukadoji Maharaj, Nagpur University, Nagpur, Dr. Ganesh Kedar, Professor and Head, Postgraduate Teaching Department, RTMNU, Nagpur. His research area is solid mechanics, operational research, and thermoelasticity. He has 29 years of teaching experience. He has completed 1 major research project and 3 minor research projects. There are around 54 research papers published to his credit in international journals and 9 in national journals. 3 students has awarded PhD in his supervision and 3 are submitted their thesis. 6 students are pursuing right now. Also, he has delivered talk in national and international conferences. Kedar sir visited to various countries for conferences. He has worked as an executive member of Indian Society Theoretical Solid Mechanics during 2018 to 2021. Now I request respected Dr. Ganesh Kedar sir to deliver his talk. Thank you.
Okay. Thank you, ma'am. Am I audible?
Yes, sir, you are audible. Please proceed.
Yeah. So, can you see my presentation?
Yes, sir, your screen is visible.
Okay. So, very good morning to all of you. And I'm at the outset very much thankful to the organizers to give me an opportunity to interact with you people. My research topic is in solid mechanics, in which we work on the thermal elasticity, which is actually the coupling of heat and the mechanical quantities. So the stress strain due to the conduction of heat in the solid, we study in this topic. So my topic is study of hysteresis and eddy current laws of one-dimensional magnetothermoelastic problem. Before going to actual my topic, I am taking an opportunity to tell you here that the Department of Mathematics, Rashtrasanta Tukadoji Maharaj, Nagpur University, Nagpur, is now the autonomous department. We have the autonomy to design our syllabus for the MSc course and also to conduct the everything regarding the examination within department. And due to this autonomy, which is conferred from this session only, 2021-22, we have designed the new syllabus for MSc, and we have tried to introduce some papers in MSc Mathematics so that this MSc degree should become the employable degree in various aspects. As the MSc people goes in mostly the teaching field, but we here introduced some papers like probability and distribution, design of experiments, decision theory and non-parametric methods, multivariate analysis, which are the part of statistics, but which is related with mathematics also. And if the students study such kind of statistical papers were here, then the MSc Mathematics people can go to the various fields like IT sector or the industries also. As well as we have also introduced some soft papers which are practical based in mathematics. In each semester, we have one paper which is known as a skill-based paper, C programming, R software, MATLAB programming, and programming with Python. So that the student can get some knowledge of the soft skills also, so that our students studying in MSc Mathematics can enter in the IT sector directly. And all these papers we have included in the syllabus at the advice of some people from IT sector like TCS. So they really appreciated, and they are very happy that we have introduced this paper in MSc Mathematics. And so at this stage, I can announce to all of you that most of the students of your college should apply to the Department of Mathematics, so that we can bring here the good people from all over, not only the Maharashtra, not only India, but also all over the globe also, so that we can provide a good citizenship to the India as well as to the globe also, who can enter in any field from the other than the teaching field also. So thank you very much to listening me patiently over here. Now I'm moving to my topic, that is study of hysteresis and eddy current loss of one-dimensional magnetothermoelastic problem. In fact, when we study the heat conduction, actually we consider only the Fourier law of heat conduction, which is established by Fourier in 1822. But this heat conduction law have the two paradoxes were there. One is there was not no coupling of heat conduction with the mechanical fields like strain, which is introduced in 1956 by Bayet, who gave the coupled equation of heat conduction in which the strain field was also included. The second paradox was due to the parabolic nature of the partial differential equation introduced by Fourier, and due to that nature of that equation, the propagation of wave or the heat wave was supposed to be infinite, but which is not actually the fact. Practically, the heat wave cannot have the infinite speed over there. So to overcome this paradox, Lord Shieldman introduced the relaxation time in the heat conduction equation in 1967. And after that, the thermal elasticity, which studies the coupling of heat conduction and the mechanical loads, that theory is known as the generalized theory of thermoelasticity. Meanwhile, in 1824, the Francois Arago, who observed that the magnetism can be induced in the materials over there. Some rotating bodies can magnetize, he observed. And the phenomena was explained by Michael Faraday later on. As well as in 1834, Heinrich Lenz stated the Lenz law, which says that the direction of the induced current flow in an object will be such that the magnetic field will oppose the change of the magnetic field that caused the current flow. Means due to the magnetic field, the current produces in the magnetized material And again, around that electric field, the magnetic field creates over there. That magnetic field, due to the current in the magnetized material, have the direction such that it opposes the original source of the magnetic field present around, and due to which actually the heat produces in the magnetized materials. And so that's why there is a relation between the magnetic field presence in the solid and the heat conduction in the solid. So that's why it is very necessary to study the magnetic effect in heat conduction, or rather you can say that the heat conduction due to the magnetic field over there. So in this present lecture, I am going to cover the part in which we have the two phenomena due to the magnetism, eddy current and hysteresis loss, due to which the heating does happen in the solid. And then we study that heat by using the theory of thermoelasticity to know the effect of the hysteresis and eddy current loss in the solid. So this is all about which I have told you that we have here the one-dimensional problem, or the thin metallic rod is considered over there, and time-dependent magnetic fields conducting currents are produced due to the rise of eddy current in the body, as well as magnetization and demagnetization, which cause the hysteresis loss. We'll see that phenomena also in detail in further coming slides over there. So this is about the history or the background of the research, in which in 2014, ISAT developed a new mathematical model for the equation of two-temperature magnetothermoelasticity theory. Rather, here the term which is we are using as a magnetothermoelasticity means thermoelasticity is the coupling of the thermal effect and the mechanical load. And magneto we are introducing because the magnetic field also causes the heating of the body. And so that the total study of this is coined as a magnetothermoelasticity theory. After that, in 2018, Das et al. Investigated the interaction of homogeneous and isotropic perfect conducting half space rotation in context with the Lord-Shulman theory, which is actually the generalized thermoelasticity, about which I have already told. In 2021, we have investigated two-dimensional problem of magnetothermoelasticity in thermosensitive finite conducting plates with eddy current loss. This paper or the study which I am presenting over here is based on the research done by Higuchi and others in 2007. They considered the eddy current loss over there and studied the static as well as the dynamic problem of thermoelasticity caused due to that eddy current loss and hysteresis loss. So now we are also taking in consideration the same problem here. The governing heat conduction equation is delta T plus W. Now this W we have taken as a heat generation. So heat generation due to only the presence of magnetic field. And so that here this W is written or taken as the heating due to the eddy current loss, and this is heating due to the hysteresis loss. I am going to consider only these two source of heating of the body, and rest is the heat conduction equation simply. Here the boundary conditions and initial conditions are taken as a temperature T is equal to 0 at all the boundaries, as well as initially the temperature is taken 0 because we are willing to study only the effect of the heating of body due to the presence of magnetic field. And so that the rest of the physical conditions on the boundaries we have considered as 0 over there. So here near that magnetic present body, we are introduced here the here the magnetic field, which is here only y coordinate we have taken, and x and z coordinate are taken 0. The electric current which is induced due to this magnetic field is given by this here, while this is the current density Jx is taken over here. So we are going to take the Maxwell's equation in consideration for the to find actually the value of Jx, so that we can have the eddy current loss over there. So here this is the eddy current. We are taking here the one a plate over here, and suppose this there is one magnet which is placed above it. So this magnet is this plate is moving with the velocity v from left to right, and here the magnetic field is induced on the body there. Due to the presence of this magnetic field, the two eddies at the leading edge, we have here the current in this direction, while at the trailing end here we have here the current direction of the current of this eddy current is in this direction over there. And due to this, the magnetic field which is produced around this eddy currents actually opposes this original magnetic field. Here at this, the eddy currents were there, the direction of this magnet will be upward, while at the trailing here in this direction, you can say, is upward, and here for this leading edge, it will be downward over there. Due to which the motion of this plate will be affected due to the Lorentz force produced over here. It is not going up. Yeah. Okay. So due to which the to keep the motion of the body as it is, some drag force is required over here, which escape in the form of Joule hit from this body. So this is all about the eddy current over here. As a result of time dependent varying, here the currents appear in the rod referred as the eddy current. The eddy current generates the resistive loss that transforms some form of energy as a kinetic energy into the heat, which is called as a Joule heat. And so this eddy current loss is taken as Jx square divided by sigma. And this quantity to be calculated over there, and which is to be considered as one of the source of heating in the body. Now the another term which we are using here is a hysteresis loss. As we know, in the ferromagnetic materials, there are some dipoles over here. And if this body comes in the contact with some magnets over there, these dipoles get aligned in the one direction. After that, if we remove the magnetic field from that, some of the dipoles get disturbed over there. And so the magnetism which is produced due to here the alignment of this dipoles again get disturbed over there. And if we place that magnetic field on the another end of it, then the dipoles get reversed over here. Means here the magnetism is in this direction due to here the first position. Now, when we change the direction of it, then the magnetization will be in this direction. And when we place the magnetic field near the ferromagnetic materials, this phenomena does happen over here. But when this phenomena just happen, it is not completely reversed in that force of it. When we have suppose started, the magnetic field is placed over there, the material get completely magnetized at this point. When we reverse the direction, it will takes here now the more magnetic field to have the nullify and in the another direction magnetization barrier. So this loop does form over there, which is known as the hysteresis loop. And here, due to this hysteresis, we can say, or due to the change in the direction of the dipoles over there and the frictional force over there, heat is produced in the solid. So that heat also we can consider as a source of heating of the body over there. So this is obviously, it depends on the number of cycles taken over here. Means the magnetization in one direction, then again in another direction, then again in the same direction, and so on. The frequency to be considered over there. So hysteresis loss is taken as the area of one hysteresis loop multiplied by the frequency, which is to be considered over here. And the product of them is assumed to be the hysteresis loss. So here the hysteresis loss is taken in the form of here, this kh mu, frequency f and hs square. So this is taken as the another source of heating of the body. By adding both of these, means We due to the eddy current loss and the Wh, which is the hysteresis loss. By adding them, we take in total the heating of the body due to the presence of magnetic field. So we have here eddy current loss and hysteresis loss, and then again we are coming to the heat conduction equation over here. Here for the study of the mechanical fields or the mechanical effect of the on the body, we consider here the Lorentz force, which is due to the presence of magnetic field, which is taken in this form over here. So these are the displacement equation of motion and the stress components to be calculated over here. We introduce here some non-dimensional variables which are given here, and due to which this problem get here the another form of it. So by taking this dimensionless quantities, and we can solve here the heat conduction equation, which is the partial differential equation with the help of Laplace and Fourier transforms. We can solve this and we can find these quantities, temperature distribution in the body, which obtained in this form. Now, in this figure, we can see the evolution of the eddy current. So Jx versus time we have taken, and at various places Z we observed it, and we can have here the variation in the AD current, you can say, which is in terms of the magnetic intensity Jx. And this is the temperature evolution for the eddy current loss, WE, at various levels, Z equal to 0, then 0.5 and 1. This is the hysteresis loss, sorry, in figure. Okay. This is temperature change with time. Now you can see here it depends on the frequencies. As if we consider the frequency F, this is the heating of the body with respect to the time. Certain time will come here that the heating gets stable over here. But we can see here the effect of the frequency. As the frequency increases over here, the heating of body does causes. So it clearly mentions the effect of the magnetic field in the heating of the solid. So due to this temperature change in the body, we can calculate here some thermal stress components, sigma xx, due to thermal effect there or the thermal stress. And magnetic stress is also calculated, and some of them is taken as a total stress produced in the body due to the heating. And obviously that heating is due to the presence of magnetic field, as we have taken the rest of the conditions as a quiescent in the statement of the problem. So this is the conclusion. The main goal of this work is to study the effect of eddy current loss and hysteresis loss on the solid. The solutions of this are obtained by using the various transforms, and we have used some softwares like MATLAB to have the calculations done over here. Here, mainly due to the exponentially decay excitation function, the eddy current and hysteresis increases at the beginning and then becomes steady after sufficient, as I have mentioned on the graph of that. And temperature increases again after certain time, it becomes stable over here. And it is very clear that the effect of magnetic field presence near the solid can be seen from the graphs over there. So this is actually the aim of the paper, to study the effect of magnetic field in the solid for the heating of it, and the mechanical changes occurs due to that heating. So these are the references I have used to prepare this presentation. So I'm very much thankful to all of you for the patience listening. Thank you. Yes.
Thank you, sir.
Suvarna.
Yes, sir. Thank you, sir. Thank you, Dr. Ganesh Kedar, sir, for the informative knowledge that you have shared on the topic study of hysteresis and eddy current loss of one-dimensional magnetothermoelastic problems. Thank you once again, sir. Dear participants, we have shared a feedback link in Telegram group. kindly fill feedback form to get your certificate. Guest is God and God is great. It's our Indian culture and our duty as well to say thank to all those who have joined this international webinar in virtual mode. For that, I request Dr. Varsha Dange ma'am, Assistant Professor, Department of Mathematics, Sri Shivaji Arts, Commerce and Science College, Rajura, to propose vote of thanks. Over
Thank
to
you,
you,
Nalge
Dange
madam.
ma'am.
Thank you, Nalge madam. Good afternoon. Good afternoon to one and all. It is my privilege to propose vote of thanks on this one-day international webinar on recent advances in mathematics. I, Dr. Varsha K. Dange, Department of Mathematics, Sri Shivaji Arts, Commerce and Science College, Rajura. First of all, extend my most sincere thanks to inaugurator of today's one-day international webinar on recent advances in mathematics, Honorable Dr. Suresh Revatkar sir, Dean of Faculty of Science and Technology, Gondwana University, Gadchiroli, who spared time from his busy schedule to grace the occasion and share his knowledge with all of us. I express my gratitude to Honorable Dr. S.M. Barkar sir, Principal, Sri Shivaji Arts, Commerce and Science College, Rajura, for his motivation and time-to-time guidance. I am thankful to Honorable Dr. Kishore Chandra Revatkar sir, Principal, Vidya Vikas College in Samudrapur, who spare time from his busy schedule. I extend a very hearty thanks to the eminent speaker, Honorable Dr. Mahisha Narayana sir, Department of Mathematics, the University of West Indies, the Mona campus, Kingston 7, Jamaica, for valuable presentation on the topic how to handle nonlinear problems in simple way. I also thankful to our another eminent speaker, Honorable Dr. Ganesh Kedar sir, Professor and Head of Department of Mathematics, RTM Nagpur University, Nagpur, for valuable insight on the topic study of hysteresis and eddy current, laws of one-dimensional magnetothermoelastic problem. I am thankful to Honorable Dr. Ladke sir, Principal, Nilkantha Rao Shinde, Science College, Bhadravati, and Chairman, Board of Studies Mathematics, Gondwana University, Gadchiroli, for gracious presence. I am thankful to Honorable Dr. Kherani sir, Vice Principal, Sri Shivaji Arts, Commerce and Science College, Rajura, for his guidance. I am thankful to Honorable Dr. Naina Shirvate, Madam, Vice Principal and Director, Vidya Vikas Education Society, Hinganghat, for gracious presence. I am thankful to IQC Coordinator, Dr. Mallesh Reddy sir, Department of Botany, for his support. I am also thankful to IQC Coordinator, respected Dr. Manohar Ambedkar sir, Vidya Vikas College, Samudrapur, for gracious presence. I especially thank to Professor Nalge Madam, Department of Chemistry, for conducting this international webinar on recent advances in mathematics. I must mention deepest sense of appreciation to Dr. Sabde Madam for her support. I also extend heartily thanks to all participants, faculties, researchers, scholars, PG students from different institutions. I must mention my deepest sense of appreciation to all my teaching and non-teaching staff members for their enormous cooperation in the organization of this one-day international webinar. Finally, I would like to thank all students. I thank a lot to one and all who contributed for this webinar directly or indirectly. Thank you. Over to Nalgi madam.
Thank you, ma'am. We are going to conclude the program by the national anthem. So I request everyone to stand at their own place in honor of the national anthem. Thank you, everyone. We hope to see you again next time. Thank you so much.